morning. Welcome to Virtual Class 11. Today is Thursday, May 7th. Let's get right to today's headlines. We have three important topics to get to today. I'm going to actually begin with topic number 3. The molar volume of a gas lab was assigned on Tuesday. Please make sure to attempt this lab and submit it before Monday, May 11th. If you have any questions, please contact me through email or through Schoology Messenger. There's also a short video clip that'll help you get a sense of what the lab was like, and of course, Virtual Class 10, which will give you some pointers on the calculations. Be sure to watch both of those before attempting to complete the lab. Also, on Tuesday, we completed the Unit 8 exam for gases. If you have not already done so, you have been locked out. Please contact me for information as to what you should do next. And now on to our main story, which is Unit 9, Thermochemistry. We're going to begin by looking at 3 quick definitions. These will kind of give you a sense of where this unit is headed and some basic framework for moving forward. So the first definition that you see up there is energy. Energy is the capacity to do work. So work could be turning a turbine, work could be driving your car. There's a bunch of things that could be classified as work. Some other terms that I want to make sure that we're aware of are heat and temperature. So if you look, heat is the energy transferred between objects at different temperatures. So what is temperature? Well, temperature is a measure of the average kinetic energy of the particles in an object. We first mentioned this in Unit 8 when we talked about the temperature of a system, and we related it to kinetic energy. And we differentiated between two objects having the same temperature, but yet still having different kinetic energies based on their differences in masses. So what we're going to do now is I'm going to send it over to our resident expert, Kevin Orlando, who's going to go into a little bit more depth about energy and specifically about the difference between an endothermic and an exothermic reaction. Take it away, Kevin. All right, thanks, Kevin. I'm standing over here at the big board to talk to you about 2 new terms, endothermic and exothermic reactions. So before I explain what's behind me, what I want to do is just go over the prefix. Endo, like entrance, means energy going into a chemical reaction. Exo, like exit, is energy coming out of a chemical reaction. So what I would like to do is to look at each of these terms and see how they factor into these graphs that show energy over the course of a reaction. So let's take a look at our first one over here on the left. So if you look, this is our exothermic reaction. And if you look at the actual graph, we start off with our reactants. They have a certain amount of energy. Then, in order to get the reaction going, we have to put in something called activation energy. It's like the lift hill on a roller coaster. It's the amount of energy you need to put in order to get this reaction started. Once the reaction starts, the energy is released, as you can see here, until you reach the product energy at the end of the reaction. So this, the left side of this, represents the reaction at the beginning. The right side represents the reaction at the end. So because we have less energy at the end of the reaction than we did at the beginning of the reaction, this is called an exothermic reaction. That red spot here represents the energy that is released during the chemical reaction. Now, compare that with an endothermic reaction. So in an endothermic reaction, we actually finish higher than we started. We still have an activation energy barrier. Often for endothermic reactions, that activation energy barrier is even larger. And we still have a difference in energy between where we started and where we ended up. In this case, that energy is absorbed. So energy is going into a reaction. It is an endothermic reaction. All right, I'm going to send it back over to the desk and we'll go through one more term before we take a look at some equations. Thank you very much, Kevin. Well, thanks, Kevin. That was cool looking and very informative. What we're going to do next is we're going to take a look at one more definition, and that definition is of enthalpy. So as you can see, enthalpy represents the total energy content of a sample, including the kinetic energy of the particles. There are 2 ways that we're going to measure enthalpy. One is using the molar heat capacity equation or using the specific heat capacity equation. And our resident scientist, Kevin Orlando, is going to go through when we're going to use each of these. Take it away, Kevin. Thanks, Kevin. All right, as my alter ego mentioned, we have two equations that we're going to go over today. One is called molar heat capacity, and the second one is called specific heat capacity. Now, if you look at the first equation, you'll notice where the term molar comes from. So I'm going to start by identifying this as moles. The very same N that we used when we talked about gas laws, and if you go all the way back to stoichiometry, the same exact idea. Now, Q is going to represent our heat energy. And heat energy is going to have a unit of joules. Of course, moles has the unit of moles. The capital C that you see right here is called the molar heat capacity constant, and it's specific to whatever material and whatever state of matter you're dealing with. So the molar heat capacity for water as a liquid might be different than the molar heat capacity for water as a solid or water as a gas. So it's a very specific unit, but it's a constant. It's not something that you're going to have to worry about changing. You'll either be looking for it in a problem or be provided it as part of the instructions. So again, molar heat capacity constant. And finally, our delta T value. Our delta T is exactly what it sounds like. Delta, if you think about math, represents change. So a delta T represents our change in temperature. Now, typically when we're dealing with molar heat capacity, that change in temperature is represented in Kelvin, but I'll show you in a second why it doesn't matter. Now, the molar heat capacity constant has a very, very broad unit. So think about this. We need joules on the left side. So the molar heat capacity constant has to have joules as part of its component. On the right side, we have to get rid of moles and Kelvin. So moles and Kelvin have to cancel out on the right side in order to leave us with just joules on the left. Let's take a look at the specific heat capacity. So again, we have heat energy. Again, that's represented by joules. Again, we have change in temperature. Change in temperature is typically in degrees Celsius, but again, it won't matter, and I'll show you why. In this case, we have our mass. So depending on what information the problem gives you, whether it gives you moles, or whether it gives you mass, or whether it gives you a molar heat capacity, or whether it gives you a specific heat capacity, you'll use one of these two equations. Just like we saw in the first equation, this is also a constant, and it's specific to every single material and what state of matter it's in. This is called the specific heat capacity constant. This has units of joules per gram degree Celsius. So on the left side of the equation, we have just joules. That means the grams and degrees Celsius that we have on the right side have to cancel out. So that's why they end up in the denominator. We need to end up with joules on the left, so we need somehow to place joules on the right side. So that's where it fits in. Now I'm going to finish with this. We talk about delta T in both of these equations, and I've mentioned several times that it really doesn't matter whether that unit is measured in degrees Celsius or Kelvin. And here's why. Think about water for a second. Water freezes at 0 degrees Celsius. And water boils at 100 degrees Celsius. So in between freezing and boiling, we change by 100 degrees Celsius. So 100 units in between freezing and boiling. Well, let's think about these units in terms of Kelvin. So 0 degrees Celsius, that is equal to 273 Kelvin, and 100 degrees Celsius, that is equal to 373 Kelvin. So the difference between freezing and boiling is 100 Kelvin. So if we're doing problems where we're looking at changes in temperature, the change is going to be the same regardless of whether you're talking about degrees Celsius or Kelvin, because the unit size is the same. The only reason we use Kelvin is because it's an absolute scale. It doesn't have a negative value. It starts at 0 Kelvin and then works up. In these problems, depending on what unit you're given for heat capacity, you're going to either use degrees Celsius or you'll use Kelvin. Either way, the change in temperature is going to be the same size and it's going to represent the same change. All right, we're going to send it back over to the desk with Kevin, who will be introducing our final clip. Thanks very much. Thanks, Kevin. That makes a lot of sense. Moles for molar heat capacity, grams for the specific heat capacity. Now, we have one more segment that we're going to do today. We're going to send it back out to our resident expert, Kevin Orlando, who's going to go through 2 example problems and let you know what tonight's homework is going to be. Take it away, Kevin. Thanks, Kevin. So our final segment today has us taking a look at 2 example problems, which will help us get started on our homework assignment. So I'm going to go over these 2 example problems and then we'll finish for today. So the first problem says, suppose a sample of sodium chloride is increased in temperature by 2.5 Kelvin when the sample absorbed 170 joules of energy as heat. Calculate the number of moles of NaCl if the molar heat capacity is 50.5 joules per Kelvin mole. So right off the bat, what you want to try and do is figure out which of the 2 equations you're going to use. Be careful. Sometimes it's confusing. Really look for the constant to tell you what equation you're using, because sometimes you might be provided grams and expected to convert it to moles in order to use the molar heat capacity equation. Hint, homework assignment. Anyway, so going back to our question, we start off with a couple of things. So I'm going to start off by writing our equation, Q equals NC delta T. So in this case, our value for Q is 170 joules, and we have N, we have C, and we have delta T. So in our case, we are actually looking for the number of moles, N, so this is our unknown. They tell us that the molar heat capacity constant for sodium chloride is 50.5 joules per Kelvin mole. And finally, they tell us that our change in temperature is just 2.5 Kelvin. So solving this equation for N, we get number of moles is equal to, so just like we did before, all 3 of these are going to come across the equal sign and end up below Q. So we're going to have Q over, 2 of these, Q over C delta T. So my Q value, 170 joules, will be divided by my value for C, 50.5 joules per Kelvin mole, and my 2.5 Kelvin. Please remember, when you're typing this into the calculator, to keep the bottom, the denominator, in parentheses, otherwise you're going to wind up with the wrong answer. So mathematically, we wind up with a value of 1.3. We're limited to just 2 significant figures. Let's do a quick check of our units. So joules on top, joules on the bottom crosses out. Kelvin on top, Kelvin on the bottom in the denominator crosses out. So we're left with our unit of moles, which is good, because that's what we were aiming to get. So the answer to our first problem is 1.3 moles, and to be consistent with what I've taught you, 1.3 moles of sodium chloride, number, unit, substance. All right, I'm going to erase this. I'll be right back so we can try our second problem. Okay, our second problem says energy in the amount of 420 joules is added to a 35-gram sample of pure water. Now, don't be thrown off. Just because it says grams doesn't automatically mean it's going to be a specific heat problem. It is in this case, but it doesn't mean that it has to be. You could be asked to go from grams to moles. So let's take a look. We have Q equals mCp delta T in this problem. Q, they tell you, is 420 joules. We have mass, we have Cp, and we have delta T. So if I continue reading the problem, it tells us that we have a 35-gram sample, and it tells us that the specific heat capacity, and that is really your best indicator for what equation you're going to use, your specific heat capacity for water is 4.184 joules per gram degrees Celsius. Now, it's a little confusing here. Don't jump to conclusions and automatically assume that if they give you a temperature, that that's your change in temperature. Those are two different things. So, reading the problem over, energy in the amount of 420 joules is added to 35-gram sample of pure water that is at a temperature of 80 degrees Celsius. The question is actually, what is the final temperature after this amount of energy has been added? So, we're actually solving for delta T. What they gave us is called T initial. That's the temperature that the water is starting at. What they're asking for is T final. In order to get from T initial to T final, we're going to have to solve for delta T. So if you look at the equation up here, here's my delta T. I'm going to move these guys down here. So I'm going to get delta T is equal to Q divided by mCp. So my value for Q, 420 joules, is going to be divided by my mass, 35 grams, and my value for Cp, which in this case is 4.184 joules over grams degrees Celsius. Plugging all of this into my calculator, of course, remembering to keep the bottom part in parentheses or to hit divided by twice, I wind up getting a change in temperature of 2.9 degrees Celsius. Now, don't jump. This is not our final answer. So in order to get our final answer, we added energy. So if we add energy, our temperature should go up. So we're going to take our T initial, which is 80.0 degrees Celsius. We're going to add this 2.9 degrees Celsius to get our T final, which in this case is 82.9 degrees Celsius. Read the questions carefully. Don't just plug in numbers and assume that because you're given a temperature, it's your delta T value. So we're going to finish up this by just letting you know what your homework assignment is. So you have 3 problems for homework. The homework assignment is called Molar Heat Capacity and Specific Heat. And I want you to do just 3 problems. So problem number 2, problem number 5, and problem number 9. So your homework, there'll be a Dropbox for this. Your homework, and this is going to be due Friday. So tomorrow, due Friday, May 8th. All right. Back over to Kevin at the desk, who's going to sign off for virtual class 11. And that about wraps it up for today. I hope you enjoyed learning all about enthalpy and thermodynamics and thermochemistry. We'll continue with this unit on Tuesday of next week. Please make sure to complete the homework assignment that I mentioned earlier. And if you haven't done so already, continue to work on your molar volume of hydrogen gas lab, which is also due on Monday. Thank you very much. I hope everyone has a great weekend, and I look forward to seeing you again next week. Bye-bye, everyone.